welcome to the lecture of this finite volume method, and where we will continue our discussion where we left in the last lecture. So, what you get, essentially combining that two, you get the discretized form as AC phi c plus summation of AF phi f equals to BC, where your AF is the flux FF, which is minus m dot f 0 plus half psi RF plus m dot f 0 plus half psi RF minus m dot f 0. Now, AC would be summation of F NBC, which is flux CF minus F NBC AF plus F NBC m dot f, and BC is QC VC. Now, to see the weakness in this formulation, so what one can do, we can, this is a multidimensional discretized system. Now, to see the weakness, one can actually simplify to problem to a one dimensional system, and then we can try to look at that what happens when. So, if you brings down to or simplify to 1D to see the weakness. So, the stencil would look like this. So, this is my C. So, that is the cell faces, this would be E, E, W, 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 and the face, this is the east, west. So, here it would be m dot E phi E, m dot W phi W. So, if you come down to that and assume the flow to be in this direction, positive direction, positive x, then this equation becomes AC phi c AE phi E AW phi W BC. So, where you can see AE is flux FE, which is half of psi RE plus m dot E. AW is flux FW, which is minus 1 plus half psi RW minus multiplied with m dot E, and AC is summation over all these faces, which is nothing but AE plus AW, and obviously your BC is QC VC. Now, what you can see, now the range of psi r is 0 to less than 2. So, the AE and AW coefficients will be opposite signs, except for the upwind scheme, where where your psi r f is 0. So, that is violating one of the basic rules for stability and causing convergence difficulties of the iterative procedure. So, same approach if you adopt in the NVA formulation, that will lead to the same shortcomings or the similar observation. Now, what is the remedy? So, the remedy is that which is kind of one can do is the deferred correction. So, this is similar to that we have discussed earlier. So, for the higher order scheme also one needs to do some sort of a deferred corrections. So, in which the coefficients will be based on upwind scheme, while the difference between HR and upwind scheme would be, so HR and upwind scheme the difference would be added as a source term. So, this would be added as a source term in the discretized equation, and the formulation the coefficient should be based on the upwind scheme. Now, this deferred correction procedure is quite simple as we have discussed to implement, because can be used in phase values calculated with upwind scheme and that calculated with the HR scheme. Now, the another issue is that it is easier to implement, but it at the same time it also lower the convergence rate. So, the convergence rate of the iterative solvers also gets affected. So, that effect can be easily estimated on an NBD formulation or the difference between the upwind line and that of the chosen for HRS scheme in the NVF formulation. So, if that difference is the HR high resolution scheme and upwind scheme, it becomes larger, then as it goes up the convergence also goes down. So, if as long as this difference is not too much, the convergence will also not be that bad or would be affected. So, that has also kind of opened up an area where scientists and engineers or rather researchers, they have put lot of effort to find out a scheme which will be free from this kind of issues. So, that gives us to discuss about two different things which is which are developed on based on this technique to overcome the reduction in the convergence rate which is associated with deferred corrections. So, there are two approach one can adopt. One is the downwind weighting factor, that is DWF method, or normalized weighting factor NWF. So, to avoid the problems which are associated with the deferred corrections, one just to improve the convergence and other stability limits. So, there are two methods one can adopt. One is based on the downwind weighting factor called DWF method, another is normalized weighting factor which is known as the NWF. Now, the implementations with respect to the equation system which will be del dot rho v phi equals to q. So, the convection with source term. So, we will do the implementation based on that, and now once you start with that equation and your discretized equation becomes like summation of f NBC m dot f phi f QC VC. So, these phi values are at cell faces and computed using HR scheme. So, the idea is that one can implement this idea in more effectively in the calculation. So, that is the whole idea. Now, to do that, that is our discretized system which we are dealing with. Now, we will first look at approach A, that is downwind weighting factor method or DWF method. So, using in that method, so the DWF factor which could be defined as phi f minus phi c divided by phi d minus phi c, which is phi f minus phi c divided by 1 minus phi c. So, you can rewrite this with the phase value like phi f equals to DWF factor multiplied with phi d plus 1 minus DWF f into phi c, which is phi c plus DWF factor multiplied with phi d minus phi c. Now, which actually redistribute the HR scheme estimate to phi f or the normalized value of phi f tilde between upwind and downwind nodes. Okay. So, the effect is reduced stencil for the discretized coefficients. Now, if the phi f, this value is computed using HR scheme which lies between phi c and phi d, the value of this DWF factor is always between 0 to 1. So, that is the restriction that you get. Now, instead of computing the DWF directly or explicitly, which uses the computed value of phi f, the DWF factor can be expressed directly from the functional relationship of HR scheme. So, one can use the functional relationship which we have already established of HR scheme to find out this DWF factor. So, instead of doing that or instead of calculating that using the calculated or computed phase value, one can do that. Now, also, and how one can do that? One can look for these different functional values in. Now, we stick to in the normalized value formulation. Here, now we look at first upwind scheme. If you look at upwind scheme, the DWF factor would be 0. If you go to second order upwind scheme, the DWF factor would be represented at phi c tilde minus 2 into 1 minus phi c tilde. So, similarly like CD, one can get this DWF factor is half. If you have from, then this DWF factor is 1 by 4 into 1 minus phi c tilde. Quick this dWA factor is 1 by 4 plus 1 by 8 minus phi c. Now, dWA factor for downward scheme would be 1. If you use mean mode, then dWA factor will have 3 different segment, like half of phi c tilde, 1 minus phi c tilde, that is for phi c lies between half and 0. Once phi c lies between half and 1, that is half, another is 0 elsewhere. Now, bounded CD, which is dWF is half and or 0, it is elsewhere where phi c tilde lies between 1 and 0. Now, similarly one can write for Osher, where dWF will have 3 segment, one is half phi c tilde 1 minus phi c tilde, which is phi c tilde less than 2 by 3, 0, 1, 0, where 2 by 3, 1 and elsewhere. Then you get SMART, which is dWA factor is in 4 different segment. One is 2 phi c tilde 1 minus phi c tilde, which is the case when phi c tilde lies between 1 by 6 and 0. Then it is 1 by 4 plus 1 divided by 8 to 1 minus phi c tilde. So, that is the 5 by 6, then 1 0 when it is lies between 5 by 6 and elsewhere. Similarly, Stoic, which will also have 4 segment for this factor. First one is 2 phi c minus 1 by phi c tilde, where phi c tilde is 1 by 6, 0, it is half, which is 1 by 5, half 1 by 4 plus 1 by 8 into 1 minus phi c tilde, which is 5 by 6, 1 and 0. So, that is 1 and elsewhere. And the muscle scheme, where the factor will have 4 segment again. First segment is phi c tilde by 1 minus phi c tilde, which is lies between 1 by 4 and 0. Then 1 by 4 into 1 minus phi c tilde, where it is lies between 1 by 4 and 3 by 4, and lastly where it is 1 elsewhere, this is 1, this is 0. So, that is what one can see the different representation of this dWA factor when you look at, now this is in NVA formulation because it is based on phi c. Now if you comparing the TBD formulation, so if you compare with TBD formulation, so what happens that this dWf factor would be half of psi Rf. Now the coefficients option from this implementation would be diagonally dominant. If you use this downwind factor based on the TBD framework, they will become diagonally dominant, and that is why this would be quite stable. Now for the completeness or the sake of completeness, the analysis of the implementation via dWf factor can be written as m dot f phi f equals to m dot f 0 dWf f plus phi f plus 1 minus dWf f plus phi c minus m dot f 0 dWf f minus phi c plus 1 dWf minus f phi f with dWf plus equals to phi f minus phi c, phi f minus phi c, and dWf f minus, which is just like your Rf and Rf minus, where the ratio between the consecutive fluxes. This is f minus if f divided by phi c minus phi f. So now the flux coefficients can be written as my flux Ff is m dot f 0 dWf plus minus m dot f 0 dWf minus, it is 1 minus dWf f minus, and flux Cf, which is going to be m dot f 0 1 minus dWf plus minus m dot f 0 dWf minus, and the discretized form of the equation, discretized equation would be AC phi c plus f NBC AF phi f equals to BC, where again your AF is flux FF, AC is summation over phases flux CF, which is minus capital F with A plus summation of small f with m dot f, and your BC is QC BC. Now, if you look at these coefficients here, they can actually end up giving you a highly unstable system of equation. So, this linear system which you will get back here, this will be quite unstable and it requires quite a bit of under relaxation to get the solution done. Now, this you can see or one can demonstrate by looking at a quick for example 1D example. Now, without loss of generality, if you assume this is the positive flow direction, then the 1D system would become AC phi C plus AE phi E plus AW phi W equals to BC, where your AE is flux FE, which is m dot E dWA plus E, then your AW is flux FW, which is m dot W 1 minus dWF minus FW, and AC is summation over phases, so which is m dot E dWF plus E plus m dot W 1 minus dWF minus W plus m dot E plus m dot W. So, the continuity equation provides you m dot E plus m dot W equals to 0, in other words m dot W equals to minus m dot E. So, these coefficients now they will become AE equals to m dot E dWF plus E, AW will become minus m dot E 1 minus dWF minus W, and AC which will become minus m dot E dWF plus E plus minus W minus 1. So, that is the simplified system for 1D where you get this. Now, here if you look at this AE and AW, they are of opposite sign. So, this is positive and this is negative. This is a serious violation to one of the basic coefficient rules. Moreover, the values of dWF factors that are larger than 0.5. So, if dWF factor which is greater than 0.5, the diagonal coefficient of AC becomes negative. So, the diagonal coefficients will be negative in sign, and which will actually can be a problem to solve through the iterative process. So, this would occur when your phi, so this is possible when phi f greater than 0.5 of phi c plus 5d, which is a situation common to all high resolution scheme for phi c greater than 0.5. In fact, the dWF moves much of the HR flux influence onto the downwind value, causing this problem, and the situation can be resemble in a effect that central difference scheme. So, it can be some sort of recovery can be made using that kind of things. So, now in the next lecture we will look at the other formulation. So, we will stop here and we will continue the discussion in the next lecture. Thank you.